Let's look at reaction mechanism, and this one is for SN2 reaction. So we're given a pairs of compounds, okay, 4 sets that we have here, and then we are asked which one will result in a faster reaction. Faster reaction is a preferable reaction, okay, generally. So let's start with the first comparison that we have, and remember this is an SN2 mechanism that we are comparing. So for an SN2, you need to have a sterically unhindered alkane, okay, or a substrate. All right, that's what you need. So alkyl halides is a good thing because the alkyl halide is the leaving group. Okay, in this case the alkyl halide, the first one, it's a secondary halide, and the first one is actually a primary halide. So in case of SN2, a primary halide is going to be better than a secondary halide because of steric hindrance, and steric hindrance means less steric hindrance, okay, because that's what you want when you're doing SN2 reaction. So which one is more favorable here? The more favorable one is the primary one. Okay, so when you're looking at the nature of the substrate, and which here your leaving group is the same. Okay, so you're not really comparing the leaving group, that's both chlorine. You're looking at whether it's primary or secondary. Okay, let's look at the next one. In the second one, we have a straight chain, and in both cases, the leaving groups are primary. Okay, and now the leaving groups are different. Okay, so in one case you have chlorine, the other case you have bromine. So which one is going to be a better leaving group? Okay, and remember, a better leaving group is a weaker base. Okay, so weaker base is equal to good leaving group. So now how do you know it's a weaker base? So if you don't know whether Cl minus or Br minus is going to be a good base or a weak base, then you convert them both into acids. Okay, so this is HCl, and then when you make the conjugate acid for Br, this is going to be HBr. Okay, so now you can compare it from the acids also, and in case of acids, you know that HBr is a stronger acid. Okay, so if this is a stronger acid, then Br is going to be the weaker conjugate base. Okay, so if Br is the weaker conjugate base, it means it's a good leaving group. Okay, so that's how you decide for this one. So if your leaving groups are different, then you have to choose for the weaker, okay, base for the leaving group. All right, let's go on to the third one. In case of the third one, in both cases, I have primary halide, and my leaving groups are the same. So that's all good. Now what I have is, of course, nucleophiles given to me. So in this case, I'm looking at two different nucleophiles. One is hydroxide, the other one is water. Now, since we're looking at an SN2 substitution, an SN2 substitution, I need to have a strong nucleophile. Why do I need a strong nucleophile? Because in SN2, the nucleophile is actually part of the reaction rate, okay, which means it's part of the transition state. It's part of the rate determining step. So all of that means that I need to have a strong nucleophile. So which one is a better nucleophile, hydroxide or H2O or water? Which one is better? Hydroxide is better. Why is it better? Because it has a negative charge. If it has a negative charge, then it means that is a stronger nucleophile. Okay, so in this case, this is going to be a better reaction, okay, not the one with the water. So that's how you would decide if you had two different nucleophiles. Let's look at the last comparison here. And in this case, in both cases, I seem to have a secondary halide, and both my halides are the same. So now what I'm looking at is my nucleophiles again. So here I have hydroxide, and here I have the hydrogen sulfide. So in the case of ASH minus and OH minus, let's compare the two. So again, with the let me erase that. And so with OH minus, this is coming from H2O, okay, and SH minus is coming from, and this arrow, by the way, this is for retrosynthesis, which means where is it coming from? And in this case, this is coming from, SH minus is coming from H2S, okay? Now remember, when we're talking about SN2, the nucleophile is very important, needs to be a good nucleophile. So there are two things we talk about a good nucleophile. A good nucleophile goes for electrophile. That's really what it is. Okay, a nucleophile goes for the electrophile. Now, when we say that you have a good nucleophile and you can have a good base, Okay, so when we say it's a good base is kind of like just getting by, all right? But a good nucleophile really is the one that goes for more electrophile. Okay, a good base actually means that it can go for protons also, because that's what bases do. Bases go for protons, all right? But a good nucleophile will not go for a proton. A good nucleophile will go for an electrophile. An electrophile is a positive center. So that's really what we are looking at, which means what for us? Okay, what does that mean? That you have a good nucleophile which does not really go for a proton. If you're not comparing it as a base, then what does a good nucleophile mean? So good nucleophile means that it should be something that is electron rich. Okay, so if something is electron rich, it's a good nucleophile. Why? Because it has more electron density. If it has more electron density, it's more likely to go towards an electrophile. All right, so that's how you can think about if you're not sure whether hydroxide or SH minus is a better nucleophile. Okay, now remember here, you're not comparing bases. Okay, you're going to compare them as nucleophiles. Okay, so how do you know whether you're comparing as bases or nucleophiles? Well, you look at the nature, okay, of the nucleophile. So I'm taking this one, but otherwise, always look for what is going to be more electron rich, okay? In the previous one where we had a hydroxide versus water, it was negative versus neutral. So that was easier to do. That was a little bit different, okay? Because now I didn't have to think about electron richness, although I did, okay, and I did say that OH minus is more electron rich because of the negative charge, okay, but it's a lot easier to do. But when you look at something like OH minus and SH minus, well, both of them have a negative charge. So what am I looking at now? So in this case, you're actually looking at the size. Okay, and when you're looking at the size of the atom, H is the same in both cases, but sulfur is going to be bigger than O. Okay, because in the periodic table, if you look down, so sulfur is below oxygen in the periodic table, so which means that SH minus is going to be better than OH minus. Why? Because of size. Okay, so the more big the size is, the more electron density it has. The more electron density it has, the better nucleophile it is. Okay, so that's how you would analyze all of these different compounds.